disturbances.
ये कहाँ गया? ये आई नहीं रहा। Can you listen me now?
Yes, sir. You're audible, sir.
But I'm unable to see that three dot to cancel that, to enable that. Where is that now?
Okay, sir. Share screen के just pass में 3 dots होंगे, sir.
Okay.
So once you share, you will get that.
Sir, screen.
सर बिल्कुल नीचे एक ग्रीन कलर का
Okay.
Yeah.
Okay, share. Remote control or disable. Disable annotation. Done. Now go to the full slide. Annotate. नहीं इसमें तो नहीं होना। Fine. You can listen me now.
Yes, sir. We can listen you, and also your video, your presentation is also okay.
Okay, but you can see me also.
Yeah.
No. But I cannot see the photos here and all that.
No, we
but
are able to see
okay.
you also, sir.
It's okay.
Yes.
I'm audible.
Yes, sir.
Okay. So should I start now?
जी बिल्कुल sir. The platform is yours now.
Okay, thank you so much. So पहले तो सभी लोगों को नमस्कार. So very good afternoon, all ladies and gentlemen. And I'm really thankful to the organizers, Professor Shobha Jain ma'am, the principal of the college, Professor Archana Jain ma'am, head of the chemistry department there, and the coordinator of the seminar, Dr. Nanda Vatia, Dr. Swagata Gupta, and other friends there. I cannot name all of them together. So it is really a pleasant moment for me to be part of this webinar there. And I'm also happy to meet my friend Dr. Sapre from GSITS. We used to meet there. Now we can meet in this seminar also. And Dr. Silavat sir has been there, and other colleagues and the students who are participating in this seminar. So as has been told that the topic of the seminar was nanoscience and technology and its impact on the society. So I have chosen the topic science, nanoscience and technology as requested by the organizers. So I chose my topic science and nanoscience and the technology. And what I'll do is I will briefly go into the historical development in nanoscience, and then the technology came out of it. And then finally, I will go give few examples of the material, the nanomaterials we have prepared in our laboratory. And some of them I will show you how these metals are prepared, for what particular application they are prepared, and how good are those materials in general, and for the sake of society's betterment. These materials can be prepared in all respects and can be manipulated for a particular application. So this is my title of the talk. It is not going, okay, fine. So this is nanoscience and technology. This is my talk, is that one from Rajaramana Center for Advanced Technology. Right. My second slide should come now. Annotate क्यों हुआ ये? Okay, fine. So nanotechnology is thinking big and working small. I'm audible. It's okay, ma'am?
Yes, sir. Yes, sir. You're
okay.
audible.
And please tell me how much time I'll get. Around say 1 hour?
यस सर,
1 घंटा चलेगा ना?
बिल्कुल बिल्कुल चलेगा
और मैं बीच में अगर हिंदी बोलूं तो चलेगा?
सर, बिल्कुल चलेगा, क्योंकि हमारे यहाँ द्विभाषी हमारे पार्टिसिपेंट्स हैं, तो इट विल बी वेरी नाइस।
वेरी नाइस ना, मैं बीच में कभी ट्राई करूंगा, और अगर कहीं पे मुझे लगा कि यहाँ पे थोड़ा समझाना है मुझे, तो मैं कोशिश करूंगा मैं हिंदी में समझाऊं,
जी
है ना?
बिल्कुल सर,
So
बिल्कुल।
this is what the nanotechnology is: thinking big and working small. Means you have to think a lot, but working at a very small scale. That is a nano scale. What is nano scale then? Nano scale is basically, nano derives from the Greek word nanos, which means dwarf or extremely small. What is that? It's basically a billionth of a meter, 10 to the minus 9 of a meter. The nanoscale involves the range from approximately 100 nanometer down to 1 nanometer. जिस नैनोमीटर स्केल की डिवाइसेस की मटेरियल की हम बात कर रहे हैं, वो 100 नैनोमीटर से 1 नैनोमीटर के बीच में होता है। हम जनरली उसी को नैनोमीटर स्केल बोलते हैं। उससे बड़ा है तो माइक्रोन में आ जाता है, दैट इज वेरी मच नोन। उससे छोटा होता है, इट्स वेरी डिफिकल्ट टू वर्क विद। सो इट इज अराउंड 1 nanometer down to 1 up to 100 nanometer. This is the scale where we work, and we talk that in nanotechnology. Nice. This is how we can manipulate the material at the atomic or molecular scale to get the size of the order of 10 to minus 9 of a meter, to have a look, to have a feel how big it is and how small it is. You can see I have given 3 examples. One child, I have given around say 1 meter. So minus 9 of a meter is C60 molecule, and plus 9 of a meter is a orbit of moon. So this is the scale where we are talking about 1 meter, and then minus 9 of a meter and plus 9 of a meter. So ultimate goal of nanotechnology is to build essentially anything from scratch, atom by atom. So we have to make materials atom by atom or molecule by molecule, the unit cell, and then get that into a material which is of your use. For a particular application, you can get that material to make that material for your application. So again, a size of a nano size, just to visualize what is the size. Nano is, if you see a tall man, the man, which is of the order of 2 billions of a nanometer. Then a dot on your finger and thumb, that is a million of a nanometer. Then you have a biological cell, which is 1,000 of a nanometer. Then you have a DNA molecule or a hydrogen atom, which is of the order of a nanometer. And then less than a nanometer, which is your atomic cell. So this is the visualization of the scale. So what we are talking about a device, we are talking about a material which is of the order of 1 nanometer to 100 nanometer range. So that is where we are working with. Again, this is not a new phenomenon. It has already been our life. If you see these nanopollutants and micropollutants, you can see these in nanoscale and micron scale. So these pollutants in water or air contamination, it is already in our day-to-day life. So we know them, but we cannot see those things. We cannot measure them in earlier days, but nowadays we can go up to the 1 nanometer. We can measure that, and we can make those material possible having the size of 1 nanometer. And I'll come to that a little later. But this is not new. If we talk about the transistor, the miniaturization of the technology has already been there, and long back in 1947, these three scientists, the Shockley, Breton, and Bardeen, they have invented the transistor in Bell Lab, 1947. So first transistor they have made, and that have revolutionized our electronics. Before that, if many of us may not be there, but few of us are older enough to see those days radios which work on the triode, tetrode, pentode valves, and these radios come in the box, big box. But after this transistor, the chipset has come, and those chips has plenty of PN junction on that. This is one PN junction here. It is one PN junction they are working on, and they got Nobel Prize for that in 1950 also. Shockley and Bardeen, all the three. And at the time, they were just looking at this PN junction, how these electrons flow from P to N or N to P, the whole comes with. And If you have a forward bias, it goes in one direction. If you have a backward bias, it goes in another direction. So those PN junction had changed, revolutionized the all electronics. And finally, today we have all the electronics, particularly the chipset and all that. You will see next slide. You will see this Moore's law. So from 1970 onwards to 2000, we have reached from few hundred chips, few hundred PN junction on a chip to 100 million chips on a transistor on a chip. This number of transistor on a chip revolutionized the memory of working of these computers today. And if you see, everybody is having their mobile in their pocket and their pen drive in their pocket, having the memory of say 1 GB, 2 GB, 3 GB and all that. So this is possible because of, this is done because of the number of transistor on a single chipset. Chipset is basically a 1 inch by 1 inch piece. You can see in all the motherboards, in all the instruments, electronic instruments, and that carries 100,000 millions of transistor on that. And this is what is called the Moore's law. Moore's basically Intel co-founder, Gordon E. Moore. He has written this book in 1965, and this rule is still working. The number of transistors on a single chipset decides the memory of that chipset, the working of that, speed of that chipset, and all that. So this is what is the revolution in the electronics at the time. And today also, this 100 million has around 500 million or so. This, if you see i8, i7 or i9, Intel chipset has come, so which has 500 millions of transistor on a single chipset. This example is just I have given because to show that how memory changes with number of transistor on a chipset, and finally we work with the, we see the speed of that chipset. Now the nanotechnology is why it is so cool. Where it changes, it changes. If you see the physical property and chemical property of a material changes with the size. If you see the bulk gold, it is a golden color. The melting point is 1064 degrees Celsius. But when it is in different nano sizes, 1 nanometer, it is brown yellow. When it is 20 nanometer, it is red. When it is say around 100 nanometer, it is purple pink. So color is changing just because of the size of the material. If you see, if it goes below a nanometer, say below 1 nanometer, the color will be a little bit brownish or black. So the physical property and chemical properties and optical properties changes with the size changes. So size of the particle is so important. It's not only the melting point also changes, optical property also changes, magnetical properties also changes. It is not very new phenomenon. Like this cup in 4th century AD, if you see this cup, if you see in a green reflected light, it looks green. When if you go in the transmitted light, it becomes red. Why? It is because this cup was made of some metal, but out at the surface of this cup, they have coated with silver and gold. But they don't know that at that time. They were not knowing the nanoparticles and all the size of that, but it was in nano size. So today, when British Museum gave this to the scientists, so they see that the image on the surface of the cup is the colloidal silver and gold particle, which were in the nanometer size. So because of that, when it is in reflected light, it gives green color, and when it is transmitted light, it is because of these colloidal silver and gold nanoparticles. But at that time when they make it, they don't know what they are doing. They are just coated with the colloidal solution of silver and gold to make that beautiful. But it is still there in the British Museum in London, okay? And you can see this. So this is the beauty of the nanoparticles. Now, that was the basic historical development in the nanomaterial. And now I will come to the basic material synthesis of these nanomaterials. particularly how these nanomaterials are made, what is their application, what are their properties. Previously, what we used to do is we go for the application for a material, synthesize that material, then measure the properties of that material, and finally go for the application, and then vice versa. But today, the technology has gone in such a direction that we first see the application. For this particular application, we need a material. For this particular application, the properties should be like this, and then we go for the synthesis of that material. So this is the beauty of uh, the development of science nowadays. So we can, for a particular application, we can develop a material. So this is the good thing nowadays. And you can have application first in your mind, then go for the properties of the material, and then synthesize that material with those properties, and finally for that application. This is the beauty. So synthesis of nanomaterial, basically two categories are there. First is top down, second is bottom up. Top down means from a bulk of a material, you can thrust that, go down to the nano size, and from bottom up, for the bottom up technique, we start with the atoms or molecules, or basically the building blocks of that material, and assemble them in such a way that you end up with a nanomaterial. So these are the two techniques, the top down and the bottom up. I'll give few examples of the materials which are being done in RRCAT. So I will take example from both, one top down and one bottom up technique. I will take three materials rather. So why these are very important? If you see these materials, so as I have told that the materials should be in 100 down to 1 nanometer range. So we can have different kind of materials, 2D structures. We can have thin films, planar quantum wall, or superlattices. In 1D structure, nanowires, quantum wires, and nanorods and nanotubes. And in 0 dimension, 0 structure, nanoparticles, and quantum dots. So these are the basically structures, means one where we have 1D confinement. Confinement means you can have only one direction there. 2D confinement in both the directions you have, because you have only in one direction you have unit cells, and 0 direction you don't have unit cell at all, nanoparticles or quantum dots, because they have hardly one atom cell size. So that's why these size dependent properties arises. And which are those properties are? First, the thermal properties, the melting temperature, as you have seen in case of gold, the melting temperature go down with the size goes down. Mechanical properties, adhesion, capillary forces, and all that changes with the size changes. Optical properties, absorption and scattering of the light changes, as you have seen that liquid stop in reflected light and transmitted light sees different colors. Then electrical properties, the tunneling current changes with the particle size. Then the magnetic property, supramagnetic effect comes when the size of the nanoparticles changes. So new properties enable new applications, means all these materials, when we have a different size, we have a different size. Can you mute your audio, please?
Excuse me.
Please mute your audio, please. New property develops new applications. New application can be rises. So three reasons why this property changes. The quantization of the energy states, that is the confinement effect. So because we are at the nanoscale, so it changes the quantum state of the energy. Means if you see the density of states and the energy, I'll show in next slide. So those quantization of state comes into the picture. It changes all the properties of the material, because we are at the quantum level. We are at the quantum level. Structural effect, the grain bound, if you have a bulk, then you have a grain bound is there. High interface volume to surface ratio will be very high, and critical length scales, because we are in nanometer. So critical length means a few atoms, few atomic units are there. So we don't have much large number of atomic cells. We have very few number of unit cells there. If you see there, I have shown the surface versus the volume. If you see the nanoparticle, in case of nanoparticle of silicon, 10% atoms are at the surface. But In the same case, same silicon, if you have in bulk size, only 0.03% atoms are at the surface. So that's why in nanoscale, when we are having a nanoscale material, so 10% will be very high, is very high percentage of the atoms at the surface. So it will be very reactive, very useful in some cases, very dangerous in some other cases. But in the bulk, only hardly 0.03% atoms are at the surface. So it is less reactive and in some cases useful, in some cases not useful. So in nanoscale materials, the surface boundary interface plays an important role. As you have seen there, because you have a large number of atoms at the surface, it's very useful in most of the cases. And boundary has there, interface is there, so it plays an important role for their application. For a particular application, it may be very, very useful. In some cases, it may be very, very harmful as well. So if you see the band diagram, I have shown the 3-dimension, 2-dimension, 1-dimension, and 0-dimension. You see how this density of state changes with energy. So 3-dimension, it is a beautiful curve, but in 2-dimension, the quantum well starts coming, and in 1-dimension, it breaks up, and in 0-dimension, it has separated. So this is what is the quantum confinement is called. So you have a different band structure for a different material at a different dimensions. So 3 dimensions, 2 dimensions, 1 dimension, and 0 dimension. The energy state changes like this. So you have basically a quantum confinement effect when you are in nano size. When you are in bulk, you have a fixed band gap. So band gap changes with size changes in the nano scale. Now, as I had told that I will take few examples of the material, and I have taken 3 examples of the material, and I have taken this high energy ball milling to show that it is top down method. Means we have started with the bulk, come down to the nano scale. So I want to tell you that one of the material here, that yarn, is mostly done by my student Nanda, and also some of her results which she has done in my laboratory there. So first I will take the example of lithium niobate. Lithium niobate is basically a non-linear optical materials. You can make NLO devices out of this material. It is very useful for making lasers. It is a laser host as well, but at the same time, it is a beautiful second harmonic generation material. Means if you have a red laser, laser in IR, but you need that laser in green, so you use this crystal, this material, and the wavelength come down to the half, and that is what, if it is 1064 angstrom, that is Nd:YAG laser, so it will become 362, 365, which is the green. So you can use that laser for other applications. You can use red laser, you can use green laser as well. So the technique for making this is, one is high energy ball milling, top down, and this is bottom up sighted gel method. So this is what we have made this material, and then make nanocomposite. So this is the pure and single phase nearly stoichiometric nanoparticles we have made by both the techniques, either top down or a bottom up. And then we take the PMMA matrix, which is polymethyl methacrylate, which is generally used for making this composite. And then these nanoparticles are put with this PMMA matrix, and you become you can have these discs of nano composites, and that can be used as a in place of single crystal, because single crystal lithium niobate is very difficult to make. It takes a lot of time. It is very expensive also. But to make the single phase nano particles and then put them in PMMA matrix and make this nano composite disc, it is very easy and very cheap as well. So you can use the disc for using this laser second harmonic generation rather than the single crystal, which is almost 20 times expensive than these discs. So, but before you go for application of these materials, once you have made the material, so you have to characterize them, which is not wise to use the material without characterizing whether the properties which you require, the properties which that application is required. So it should be there with that material. So we characterize those materials with X-ray to see the structure. Then we go for the electron microscopy and neutron microscopy to see that whether the particular unit cell is of the order of that and the size of the nanometer, size of that particle, how much nanometer it is, and in that particular size whether that particular application is fulfilled or not. So we go for the material characterization by doing X-rays and powder X-ray, and then it is for the top-down method material, and it is for the bottom-up prepared material. So we can see both of the materials; they are really good, and then see the TEM images. So you can see the size of the nanoparticles, whether they are of good use, useful size, whether they can be used for that particular application or not. And then you see the DLS particle dynamic light scattering program in the machine to see whether where this size falls, because it is basically a range. It will not be of single size. Say in this case it is 30 to 60 nanometers, which is enough for making second harmonic generation this and second harmonic generation application. The size is enough. It should be less than 100 nanometers. So it is coming about 30 to 60 nanometers. तो इस एप्लीकेशन के लिए मैंने कभी बीच में बोला था कि it should be 100 nanometer down to 1 nanometer. So 30 से 60 nanometer के जो range के molecules हैं, particles हैं, they are of course useful for this application. है ना? So this is the optical absorption to see whether this will be used for that particular application, because it shows the band gap. So band gap should be in such a way, such range that it should not interfere with the device, because we are using for an optical device. So SHG is optical device, second harmonic generation. So band gap should be in the range. So this cut, this shows the UV cut, it shows the band gap of the material. Similarly, this shift is shifting towards the lower wavelength, means blue shift. Blue shift means the band gap is increasing. So band gap. So increased band gap means the lower cutoff should UV cutoff. So the higher band gap. So higher band gap means it is useful for our application of second harmonic generation. Second, this is the YAG nanoparticle. And this is the work done by most of the work is done by Nanda, who is sitting there. She has done in RRCAT. So YAG is one of the extensively used solid state laser material. It's very useful solid state host material, and it is most of the lasers in IR region are made by this material. This is so important, but making single crystal of this material is very, very expensive, because the melting point of India is 2000, around 2000 degrees Celsius. So India is basically yttrium, aluminum, garnet. So, but making nanoparticles of that and then making those composites with PMMA is very easy, very non-expensive also, but making single crystal is very difficult. It takes a week time to grow one crystal, and then temperature is very high. The machine you require is of the order of 5 to 6 crore rupees for that puller. But nowadays, when we make nanoparticles of that, and then that is made by the glycol method, which is very low temperature method, around 800 degrees Celsius. So you can grow the make these nanoparticles and use that in place of the crystal. In place of the crystal, this can be used. Okay, so this is the flow chart of rare earth doped YAG preparation, because we use to dope all rare earth in this ND and all other rare earth materials, and then make that particular, because the wavelength of that laser changes with this Re atom in that, Re molecule in that. So this is basically the flow diagram, how these, and finally we end up with the nanocrystals of Re doped YAG, and that can be used making those composites discs or rods and make the laser out of it. So again, to characterize those materials, what has been made. So you use X-rays, you use XRDs, you use EDAX to see that whether the material is of the same quality or same concentration or same basic structure, So we use X-rays, then ADAX, and then same micrograph also show that whether the size of the crystallites are of the order of nanometers, that is down to 100 nanometer or so. So then only it is useful. So it is well below the 100 nanometers. And then transmission electron micrograph, again, so the size. So here we see that 25 to 50 nanometer size of the nanoparticles has been achieved. And the when we anneal those materials up to this temperature, so we can end up with this size. So again, if you go higher temperature, the size will increase. But again, the size is well down to 100 nanometer, below 100 nanometer, so it can be used. So this is the work done by Nanda. Most of the work is done by the Nanda. High resolution again shows that how these structures are there, and this correspond to selected area diffraction. If you see this corresponding selected area diffraction, it tells that it is beautifully structured, and this is the desired structure what we were trying to make. And then I will take one example of carbon nanotube. Mostly this work was done at the Korea Institute of Chemical Technology in Daejeon, South Korea. And one of my colleagues worked with this with me, and he has made these carbon nanotubes. The carbon nanotubes are very useful nowadays. And if you go for the medical use of these carbon nanotubes for the drug delivery system, it is very useful because nowadays, particularly for the cancer treatment, you need to, instead of going for chemotherapy, chemotherapy goes in the whole body. So it affects many organs together, many cells together. But if you go for a particular cell, because few cells are having those cancerous problems, but rest of the cells are the good cells, but all the cells damages with the chemotherapy. But in this carbon nanotube, you can deliver the drug to that particular cell where the cancer is there. So you can use these carbon tubes for carbon nanotubes for delivering the drug for that particular cell to kill the cancerous cell. So rest of the cell will be okay. While rest of the cell will not get damaged. So this is one of the usefulness of this carbon nanotubes. And other technologies other than this is making very hard surface, very strong surface by using this. So these carbon nanotubes are very useful. This is a technique what we were using, how to make those carbon, chemical vapor deposition technique was used to make these carbon nanotubes there. And this is what is the flow chart of making these carbon nanotubes. I will not go detail into this because the technical things. So, and then once you have made those carbon nanotubes, so you have to again characterize them, whether you have end up with the actual quality of an actual structure of the carbon nanotube. So if you see this, these are two graphite peaks, this and this, but this one is the CNT peak. So if this peak is around 44 degree to theta, so it shows that yes, you have end up with the carbon nanotube, and this will come only this because the most part of that is graphite. So this is first peak at the 002 is the graphite peak, and 004 is again at 26 and 54, they are the graphite peak. But at 44, if you have a peak here, so it is a carbon nanotube. So that is sufficient. Once you have this much peak, it is sufficient that you have end up with the carbon nanotubes along with the graphite. So you have to separate those graphites from the carbon nanotube and end up with the useful carbon nanotube. So this, now this is the SEM image of the purified multi-wall nanotubes. So these are the carbon nanotubes, you can see them. So apart from the graphite will be in bulk, but carbon nanotubes will be in the form of tubes. So these all tubes are carbon nanotubes. Only thing is they are multi-walled. They are not single-walled because you have plenty of them, but they have multi-walled. They are not a single-walled. So if you see them, now you can see that this is again a single tube. You can see the electron diffraction pattern, high resolution transmission electron diffraction pattern, an image of that, and then the diffraction of that shows that yes, it is a single walled carbon nanotube, and this is again a multiple wall carbon nanotube. So you can use this tube, this type of tube. If you have a millimeter or a 2 millimeter of that, it is sufficient to work on that, and that is sufficient for even a drug delivery system. On the tip of that, if you have 2-3 millimeter of carbon nanotube, you can use that as the tip of the tube and then use that uh, tube for drug delivery in the body. As I have told that this is the size dependent property of that comes because of the number of atoms on the surface, which is very reactive. So, because it is 10% of the atoms are at the surface. So most of the time they are very reactive. So nanoparticles could be inhaled, swallowed, or absorbed through skins or deliberately ejected because they are very reactive. Even if it is inhaled a little bit, it is very, very dangerous. So it is really health issue is a big challenge in the case of these nanotechnology, nanomaterials, because of their very high reactiveness on because of the surface volume to surface ratio of that material. Then environmental issues also, nanoparticles accumulate in soil because it cannot be destroyed. If it is accumulated in soil, water, plant, or traditional filters, it is too big to catch them because they are so small. It is really difficult to to separate them because they are very small. Can you please okay. Then the new risk assessment methods are needed. So international or national level agencies are beginning to study the risk. Results will lead to the new regulations because we have to make new regulations to work on the nanomaterials and to see, because in most of the time it is really difficult to see the effect of that material in a direct way. But indirectly, they are very, very harmful, very, very harmful. Because just because you cannot see them, you cannot really separate them because of their size problem and all that. So this is what the nanoscience and nanotechnology journey. If you see the journey of this technology, the passive nanostructures way back in says around 2000. So you see them. So disperse and contact nanostructures has been worked in around 2000, aerosols and colloids. Then products incorporating nanostructures, coatings and nanoparticles has been working since 2000. Then comes to active nanostructures, bioactive health effects and targeted drug delivery system. As I had told, 2005 onwards, people are working on the, particularly the biologists and physicists are working together to work on this targeted drug delivery systems and all that, because physical and chemical activities of those particles is very, very useful, and particularly a little bit change in the magnetic structure of that material. So it gives a lot of electric field, and to kill those cells just by using the electric current, not even in some cases, not even the drug. So that electric current is enough to kill those cells by using those gold particles. In case of in cancer, it is sometimes gold nanoparticles are being used to achieve those current range to kill the cancerous cell. Then systems of nanosystems. So with 3D networking and new hierarchical architecture, robotics, and evolution, it has come around 2010. A lot of work is going on in this direction. Then the molecular nanosystems, 2015 to 2020 onwards. So a lot of molecular devices are being designed. Inside the molecule, if you can design a motor, so this is what is the nanotechnology nowadays. But this is very high-end research, and still people are working on this, and I think it will go in good direction in future, near future. So some of the application of the nanotechnology are the systems where we can manipulate the properties of the material as per our requirement. As I've told in my talk, that we can manipulate the properties of the material by just changing the size, by just changing the corresponding material and the properties of that material, the mechanical strength, the structure, the electrical properties, magnetic properties, optical properties, carbon-based nanosystems for many applications in space and household. As I have told you, in some of the space suits, you use these carbon nano materials. So these space suits are being made by this. So it will not get you cannot, you don't have to wash them really, because nothing can go and stitch to them. तो दिस इज वेरी यूजफुल. सो स्पेस शूट में भी आजकल जैसे इसको यूज करते हैं कार्बन नैनो ट्यूब्स को, तो उसमें क्या होता है, कुछ लगता नहीं है, धूल भी नहीं लगती है उसमें, कुछ पानी भी नहीं लगता. तो ये अगर वो 6 महीने के लिए वहां रह रहा है, 7 वर्ष के लिए वहां रह रहा है, तो यू डोंट हैव टू वॉश दम. वॉश करने के लिए वापस पृथ्वी भी आओ तभी वॉश करो. हाउस होल्ड में बहुत सारी चीजें हैं जो कि अभी कार्बन नैनो ट्यूब से आने वाली है, अभी तो नहीं है बट आने वाली है फ्यूचर में, तो जो कि हाई टेम्परेचर के लिए है या रोबर्टनेस के लिए हैं, या इवन क्लॉथ्स में भी कुछ दिनों बाद हो सकता है कि नैनो पार्टिकल्स के यूज में कुछ कपड़े ऐसे आ जाए जो कि स्पेस शूट में होता है, यहाँ भी हम लोग यूज कर रहे हैं, तो शायद ये संभव है कि हमें कपड़े धोने की जरूरत ही ना पड़े. Then medicine and drug delivery system, as I told you, size dependent drug compositions for very quick relief and action. अभी कुछ ड्रग्स ऐसे हैं जो कि नैनो में आना शुरू हो गई हैं. जैसे मैं एक एग्जांपल दूं आपको, जैसे हम लोग पहले यूज करते थे एलोपैथी, होम्योपैथी एंड तीसरा जो है आयुर्वेद. तो होम्योपैथी में जनरली क्या होता है, होम्योपैथी में डाइल्यूशन काम करता है. डाइल्यूशन ऑफ दैट पर्टिकुलर मॉलिक्यूल इज वेरी वेरी हाई. डाइल्यूशन बोलते हैं ना, तो 10 लाख 15 लाख 20 लाख, तो उसका डाइल्यूशन होता है. जितना डाइल्यूट होगा उतना एक्टिव होगा. तो सिमिलरली इस केस में साइज भी जितना छोटा होता है उतना एक्टिव होता है, क्योंकि सरफेस पे बहुत ज्यादा नंबर ऑफ आइटम्स है. तो इसको यूज किया जा सकता है जैसे पेन रिलीफ में. अगर कोई पेन रिलीफ की टैबलेट है, अगर हम उसको माइक्रोन साइज का टैबलेट लेते हैं, तो हमको सपोज 500 मिलीग्राम की टैबलेट लेनी पड़ती है. से फॉर एग्जांपल हम कॉम्बिफ्लैम लेते हैं, तो 500 mg की कॉम्बिफ्लैम लेते हैं. लेकिन अगर वो नैनो साइज में उसके पार्टिकल हो या सब माइक्रोन में भी हो, तो उसका इफेक्ट बढ़ जाएगा, उसका एक्शन जो है, बिकॉज इट इज सो एक्टिव. तो हमें 10 mg में काम चल सकता है, 2 mg में काम चल सकता है. अगर नैनोमीटर साइज में हो तो सकता है 1 mg में ही हमारा काम चल जाए, अगर क्विक रिलीफ के लिए जरूरत हो. लेकिन इसमें भी रिसर्च की जरूरत है कि ये डेंजरस भी है. अगर ये हमने नैनो में तो बना लिया, इसने एक्शन भी कर लिया, लेकिन इट इज सो डेंजरस. अगर ये बॉडी में अंदर चला जाता है, इट्स डिफिकल्ट टू गेट आउट ऑफ इट. बाकी तो माइक्रोन साइज के पार्टिकल आपके बाहर आ जाएंगे, बट इसको बाहर आने में दिक्कत हो सकता है, कुछ और को डैमेज कर दे. उसने रिलीफ तो दिया, बट हो सकता है. तो इस पे अभी वर्क चल रहा है. अभी हम नैनो में इसमें नहीं गए, कुछ माइक्रोन साइज में तो अभी कुछ मॉलिक्यूल्स आ गए हैं दवाइयों के, बट नैनो साइज में अभी इस पे वर्क चल रहा है, बिकॉज इट इज वेरी हार्मफुल. एट द सेम टाइम स्मॉल साइज हार्मफुल, जैसे मैंने लिखा है यहाँ पे, इट इज वेरी हार्मफुल ऑल्सो बिकॉज ऑफ इट्स रिएक्टिव कैरेक्टरिस्टिक्स. ये बहुत ज्यादा रिएक्टिव है, इस पे काम करने की जरूरत है. बट अदरवाइज इट इज वेरी गुड फॉर क्विक रिलीफ, बिकॉज जितना ज्यादा एक्टिव होगा उतना जल्दी ये रिलीफ देगा. बट एट द सेम टाइम वी हैव टू लुक इनटू द एक्चुअल जो उसका प्रैक्टिकल पर्पज है वो सॉल्व तो हो रहा है, लेकिन इट शुड नॉट बी वेरी हार्मफुल ऑल्सो. So this was all about the application of nanoparticles and nanotechnology. So science and technology of nanometer science is really good in one sense. It is very high-end research. It needs a lot of research to do. Now, अभी ये बहुत कुछ इसमें बाकी है, बट बहुत सारी चीजें मार्केट में हैं, बहुत सारी चीजें आ गई हैं, लेकिन बहुत सारी चीजें अभी बाकी हैं. तो हमें बहुत ज्यादा इसमें काम करने की अभी जरूरत है. तो जो न्यू जनरेशन यहाँ पे है, जो नए स्टूडेंट्स हैं, मैं उनसे यही रिक्वेस्ट करूंगा कि यस, वर्क ऑन दिस टेक्नोलॉजी. इट्स वेरी गुड एंड सर्टेनली फ्यूचर तो है नैनो टेक्नोलॉजी का, बट इट इज रिक्वायर्स लॉट ऑफ रिसर्च इन दिस. सो दिस इज ऑल अबाउट my talk, and the summary of my talk is basically the field of nanotechnology offers the possibility of transforming the materials application, as I've told you, because you are dealing with the size and you are playing with those materials at the different size level, and then for a particular application you need that material, so you can play with manipulate that material and get your material for that particular application. And nanotechnology is not a single subject technology. It integrates physics, chemistry, biology, material science, material engineering, and art sciences. The structure and property changes with size distribution of the particle, as I have shown you. So a lot of property changes with the size change, and the possible design materials for a specific application is possible in this case, because you can design the material for a particular application. And the application of materials in medicine, automobiles, food, textiles, cosmetics, and whatnot. Everywhere you can use these materials when you make those materials as per your requirement for your particular application. You can really design the materials in different ways. And finally, the nanotechnology is the futuristic technology. It requires a lot of research, a lot of efforts to work with. And thank you very much. Thank you so much. Puna?
Thanks a lot, sir. Sir, can you please unshare your screen now so that we can view you?
Okay. Share.
Thanks a lot, sir, for your elaborate scientific talk. It
Okay,
was a nice journey
just a minute.
through your scientific
Stop
endeavor.
share.
Thanks a lot, sir.
Okay, thank you so much.
Now I will invite Dr. Nanda Bhatia for the question answer session. We are having some questions in the chat.
Sure.
Some of the participants want to know about carbon nanotube and silicon nanotube. What is the difference between carbon nanotube and silicon nanotube, and which is more जिसकी application बहुत ज़्यादा अच्छी है, silicon और carbon?
Okay. पहली बात तो ये है कि carbon nanotubes is made of carbon. Silicon nanotubes are made of silicon. Okay. But the carbon nanotube has plenty of applications. Carbon nanotube के बहुत सारे applications हैं because carbon itself is material which is nature friendly. Okay. But at the same time, silicon is not that nature friendly because in few cases, silicon nanotube have very few applications. And I'll say silicon nanotubes are not really that useful compared to carbon nanotubes. और इतना यूजफुलनेस सिलिकॉन नैनोट्यूब का नहीं है। जिन्होंने ये बोला है उनको मैं एक चीज कहना चाहूंगा कि सिलिकॉन नैनोट्यूब जनरली सिर्फ रिसर्च के लिए तो लोगों ने लैब्स में बनाई है, बट इट इज नॉट ऑफ द प्रैक्टिकल एप्लीकेशन।
ओके सर, नेक्स्ट हमारे एक पार्टिसिपेंट ने क्वेश्चन किया है लिथियम नायोबिएट, उसमें सिंगल क्रिस्टल ग्रोथ, उसकी एप्लीकेशंस।
मैंने अभी एप्लीकेशन गिनाए थे। सेकंड हार्मोनिक जनरेशन लेजर में अगर आपके पास इंफ्रारेड लेजर होती है तो कुछ एप्लीकेशन के लिए तो इंफ्रारेड लेजर आपको चाहिए, बट इन मेनी केसेस यू डोंट नीड दैट। तो आपको उसका सेकंड हार्मोनिक चाहिए होता है, यानी हाफ वेवलेंथ चाहिए होती है कि जो आपको विजिबल में आ जाए। तो सपोज एनडीआर की जो लेजर है उसका जो वेवलेंथ है 1064 एंगस्ट्रॉम होता है ना। तो अगर उसको हाफ करना हो तो लिथियम नाइट्रेट का क्रिस्टल एक बीच में लगा देते हैं, उसको बोलते हैं सेकंड हार्मोनिक जनरेशन, यानी सेकंड हार्मोनिक कर दिया आपने, जैसे हाफ कर दिया। अब ये आ गई विजिबल में, विजिबल में आ गई। तो उस विजिबल को जैसे आई ऑपरेशन करना है तो जनरली एनडीआर लेजर नहीं यूज होगी, एनडीआर लेजर यूज होगी लेकिन बीच में एक लिथियम नाइट्रेट का क्रिस्टल डाल देंगे। अब वो विजिबल में आ गई, तब आप आई ऑपरेशन कर सकते हैं। या आदमी के अंदर का अगर कोई ऑपरेशन करना है या यूज करना है इस लेजर को तो आप आईआर नहीं डाल सकते, आपको जो है विजिबल रेंज में आना पड़ेगा, जलाएगा नहीं। तो ये इसका मेन यूज लिथियम नाइट्रेट का ये है। और एक यूज और भी है कि ये लिथियम नाइट्रेट क्रिस्टल अगर आप सेल्फ ट्यून्ड बना देते हैं जिससे लेजर भी निकलती है, सेकंड हार्मोनिक भी देता है और लेजर भी देता है।
सर इस सीरीज के और एलिमेंट्स को लेकर भी हम ये वर्क कर सकते हैं लिथियम के अलावा? लिथियम
नाइट्रेट में पोटेशियम नाइट्रेट है, पोटेशियम नाइट्रेट भी यूज होता है और केटीपी यूज होता है पोटेशियम के अलावा। और इसमें जो है बेरियम बीटा बोरेट भी यूज होता है। ये डिपेंड करता है कि आप किस लेजर के लिए काम कर रहे हैं। देखिए सारे के सारे लेजर को हाफ करना हो तो लिथियम नाइट्रेट नहीं यूज होगा, है ना। कभी कभी जो है दूसरा क्रिस्टल जैसे केटीपी कहीं पे चाहिए होगा, जैसे केपीडी कहीं पे चाहिए होता है, पोटेशियम डाइहाइड्रोजन फॉस्फेट। तो ये डिपेंड करता है किस वेवलेंथ को आपको हाफ करना है या हाफ करना है, फिर उसका भी हाफ करना है। थर्ड हार्मोनिक भी आता है, फोर्थ हार्मोनिक भी आता है, और उसको जो है यूवी में ले जाना है। कभी कभी किसी केस में क्या चाहिए होता है, आपको यूवी लेजर चाहिए तो उसको यूवी में ले जाना है तो फोर्थ हार्मोनिक आ जाएगा, थर्ड हार्मोनिक आ जाएगा। तो वहां फिर आपको दूसरा क्रिस्टल चाहिए होता है, वहां पे केडीपी लगता है, पोटेशियम डाइहाइड्रोजन फॉस्फेट लगता है। एक लिथियम नाइट्रेट लगा दिया, फिर एक केडीपी लगा दिया, यू हैव नाउ यूवी लेजर।
राइट। वैसे हम रुबिडियम सीजियम भी ले सकते हैं, उसकी भी कुछ एप्लीकेशंस हो सकती है।
रुबिडियम सीजियम भी ले सकते हैं, लेकिन उनके साथ दिक्कतें कुछ और हैं। उनके साथ दिक्कतें क्या है कि उनका एब्जॉर्प्शन बहुत ज्यादा है, एब्जॉर्प्शन कोएफिशिएंट लिथियम नाइट्रेट से बहुत ज्यादा है, तो उसमें फिर वो दिक्कत आ जाती है। आपकी आधे लेजर की एनर्जी तो वो एब्जॉर्ब कर देती है। आप समझिए ना, ले सकती है, बना सकते हैं, लेकिन ये इनका एब्जॉर्प्शन बहुत ज्यादा होता है। द एब्जॉर्प्शन कोएफिशिएंट ऑफ ए मटेरियल इज वन ऑफ द इंपॉर्टेंट फेनोमेना, क्योंकि आपका एनर्जी तो वही लॉस हो गई एब्जॉर्प्शन में, तो
हाँ,
बची
वो तो
कुछ नहीं,
absorb कर,
है ना ये।
सर और कुछ पार्टिसिपेंट्स बायोलॉजी फील्ड से हैं, जूलॉजी से, तो वो इसके एप्लीकेशन कॉस्मेटिक्स में और टिश्यू इंजीनियरिंग में जानना था।
एक पहला तो मैं एक नेगेटिव बात करना चाहूंगा, जैसे हमारी जो बहन जी लोग हैं, माता जी हैं, एक सिंदूर यूज करती है ना। सिंदूर क्या होता है बेसिकली, आप तो केमिस्ट्री के हैं,
रेड लेड,
है ना, लेड ऑक्साइड होता है। लेड ऑक्साइड को आपने ये लगाया तो चलता है ना, क्योंकि माइक्रोन साइज में है। अगर उसको नैनो साइज का कर देंगे तो क्या होगा, सब मर जाएंगे, है ना। बहन जी भी गई, माता जी भी गए, साथ भी गए, है ना, क्योंकि अगर थोड़ा भी मुंह में आ गया और नैनो साइज में वो है, वो इतना रिएक्टिव होगा कि उनसे सरफेस, मैंने कहा ना 10% एटम सरफेस पे है, इज वेरी रिएक्टिव, और वो बॉडी से बाहर भी नहीं आता है। सबसे बड़ी प्रॉब्लम क्या है, वो बॉडी से बाहर नहीं आता, इट विल किल। ये तो नेगेटिव हो गया, है ना। पॉजिटिव बताता हूँ मैं। पॉजिटिव में क्या है, क्रीम में आजकल कुछ सब माइक्रोन साइज के पार्टिकल लोगों ने डालना शुरू कर दिया, और आजकल भैंस को भी गोरी बनाने वाला जो क्रीम आता है उसमें लोग क्लेम करते हैं ना कि हमने ये डाल दिया, उसमें नैनो डाल दिया। नैनो तो नहीं होता है, नैनो तो अभी कॉस्मेटिक में यूज करने का सरकार से परमिशन नहीं है, बट सब माइक्रोन में आ गए हैं, एंड इट रियली वर्क्स इन सम केसेस। ये थोड़ा गोरापन भी देता है, थोड़ा आपके जो पिंपल्स को वो करने के लिए अभी कुछ मेडिसिन आई हैं जो रियली इट वर्क्स। और ये तो हो गया एक कॉस्मेटिक्स में। और क्या बोला था कॉस्मेटिक्स के अलावा? मेडिसिन मैंने आपको बता दिया, ड्रग डिलीवरी। हाँ जी,
टिश्यू इंजीनियरिंग,
टिश्यू,
टिश्यू इंजीनियरिंग।
अच्छा, टिश्यू इंजीनियरिंग इज डिफरेंट सब्जेक्ट। टिश्यू इंजीनियरिंग में आप नैनो के रूप में नहीं कर सकते। टिश्यू इंजीनियरिंग इज ए सब्जेक्ट वर्किंग एट द डीएनए लेवल, है ना, और आपको वहां पे नैनो नहीं, वहां पे तो कोई भी साइज का रोल नहीं है। वहां पे रोल है कि आपको डिजाइन करना है, आपको चेंज करना है डीएनए स्ट्रक्चर, सो साइज का रोल वहां पे नहीं है। नैनो हैज नथिंग टू डू विद दैट, वो साइज इंजीनियरिंग नहीं है, वो डीएनए इंजीनियरिंग है। यहाँ पे आपके डीएनए में डीएनए के मॉलिक्यूल को चेंज करना है, और ये आजकल हो रहा है। डीएनए मॉलिक्यूल के आप स्ट्रक्चर चेंज करते हैं, बट इट इज नॉट बिकॉज ऑफ साइज। साइज हैज नथिंग टू डू विद दैट।
तो सर डीएनए का मॉलिक्यूल अगर चेंज होगा तो फिर जेनेटिक्स चेंज हो जाएगी?
होता है ना, करते हैं ना लोग आजकल। जो आजकल कुछ बीमारी ठीक करने के लिए, जो जेनेटिक बीमारियां ठीक करने के लिए आजकल वो जो है डीएनए इंजीनियरिंग की जाती है। और बहुत सारी बीमारियां हैं जो जेनेटिक बीमारियां होती हैं, तो डीएनए स्ट्रक्चर चेंज करके वो बीमारियां खत्म की जा रही हैं आजकल। पर वहां पे नैनो का कोई रोल नहीं, नैनो हैज नथिंग टू डू विद दैट।
ओके फाइन सर। सर ये कुछ क्वेश्चन थे, और एक क्वेश्चन और है, डिफेंस में इसका यूज।
डिफेंस में तो बहुत यूज है नैनो का। डिफेंस में नैनो का सबसे बड़ा यूज है। डिफेंस में कुछ कोटिंग्स ऐसी आ गई हैं, जैसे आजकल आपने सुना होगा स्टील प्लेन, है ना, जो दिखाई नहीं देता है, तो उसमें जो कोटिंग होती है उस पे, वो कुछ ऐसी कोटिंग होती है कि जिससे कि कोई भी उस पर रेज जाए, चाहे आईआर जाए चाहे लेजर जाए, वो उसको एब्जॉर्ब कर देती है। एब्जॉर्ब कर देती है तो वापस जो है रडार पे नहीं जाता है। तो जब तक कोई भी चीज ऑब्जेक्ट से रिफ्लेक्ट होकर रडार पे ना जाए तो इसको देख नहीं सकते। तो आजकल कुछ ऐसी कोटिंग्स आ गई हैं जो नैनो में है। उसको स्टील प्लेन आपने सुना होगा, भारत के पास तो अभी नहीं है, लेकिन अमेरिका के पास है, चाइना के पास है, रशिया के पास है। वो प्लेन दिखाई नहीं देता है, जनरली बिकॉज ऑफ दिस कोटिंग ऑफ दिस मटेरियल्स। ये भी है। फिर उसका स्ट्रक्चर भी कुछ इस तरह से बना देते हैं, उसका सरफेस एरिया कुछ इस तरह से कर देते हैं, कम कर देते हैं, सो दैट कोई भी चीज जो प्रोब उस पर जाए, वो प्रोब जो है उससे रिफ्लेक्ट होके वापस न जाए। तो आईआर भी वापस नहीं जाता है, लेजर भी वापस नहीं जाती है, सो दैट यू कैन नॉट सी देम। और अगर बाद में कभी प्लेन तो बहुत दूर चला गया, तब आपका अगर कुछ थोड़ा बहुत इंफॉर्मेशन आएगी, बट इट इज टू लेट टू गेट द इंफॉर्मेशन। एक तो ये बहुत अच्छा यूज है। दूसरा यूज अभी कुछ मटेरियल्स ऐसे हैं जो नैनो फॉर्म में है, जो कि अभी उसको एमुलेशन के लिए भी यूज किया जाएगा फ्यूचर में। अभी वहां तक तो पहुंचे नहीं है, बट जो हमें कभी बम का गोला सेवरल 100 किलोग्राम में बनाना था, कल हमको जो है कुछ किलोग्राम में ही वो काम कर जाएगा, just because of the size of the particle which is quite less than those bulk sizes। तो ये एक फीचर। लेकिन अभी सबसे ज्यादा यूज इसका जो है कोटिंग में ही यूज हो रहा है, प्लेन पे कोटिंग में यूज होता है। मिसाइल्स के आगे से कोटिंग, जैसे जिंक सेलेनाइड की कोटिंग करते हैं मिसाइल के डोम पे, तो मिसाइल अगर उस स्पीड से जा रही है जिस स्पीड से उसको स्पेस में जाना है और अर्थ के एटमॉस्फेयर में जाना है तो जल जाएगा। तो उसके जिंक सेलेनाइड और जिंक सेलेनाइड एंड जिंक सल्फाइड, ये दोनों सल्फाइड एंड सेलेनाइड का कॉम्बिनेशन लगाते हैं और उसको पार्टिकल साइज कम रखते हैं, सो दैट जो फ्रिक्शन की वजह से जो एनर्जी पैदा होती है, जो हीट पैदा होती है, वो जलता नहीं है। नहीं तो वो तो वहीं जल जाएगा पहले, जो एटमॉस्फेयर में जाएगा उस स्पीड के साथ, तो वो वहीं जल जाएगा। तो आजकल वो नैनो पार्टिकल्स का उसमें कोटिंग करते हैं सो दैट इट एब्जॉर्ब दैट मच हीट, क्योंकि कभी तो 5000 से 10,000 डिग्री सेल्सियस तक की हीट भी हो जाती है। इट सपोर्ट्स टू एब्जॉर्ब दैट हीट। तो जिंक सल्फाइड और सेलेनाइड के नैनो पार्टिकल्स की कोटिंग करते थे। पहले क्रिस्टल लगाते थे, अब क्रिस्टल की बहुत महंगा पड़ता था, डोम क्रिस्टल का ही बनाना, इट टेक्स सेवरल मंथ्स टू मेक वन डोम। आजकल नैनो क्रिस्टल्स का ये पाउडर बना दे, जैसे हमने पाउडर बनाया, जैसे आपने बनाया इंडिया का पाउडर, उस पाउडर की कोटिंग उसमें कर देते हैं सल्फाइड की। तो इट इज मोर देन सफिशिएंट इंस्टेड ऑफ दो सिंगल क्रिस्टल्स, जो कि करोड़ों रुपए का एक सिंगल क्रिस्टल का डोम पड़ता था, अब हजारों रुपए में नहीं तो कम से कम 1 लाख रुपए में हो जाएगा, समझना है।
Okay, sir. Thank you, sir. So
Thank you so
this
much.
is the
Welcome.
end of our question answer session.
Question.
Now I hand over this session to Dr. Swagata Gupta, madam.
Hello, I have a
Thank you
question.
so much.
Could you please
Thanks a
give me
lot, sir.
opportunity?
Yeah, thanks a lot, sir. There are a lot of questions in the chat box, लेकिन समय की मर्यादा को देखते हुए हम उनको हमारे WhatsApp ग्रुप में ले लेंगे और आपके पास भेज देंगे।
Oh, sure.
And then
No
again,
problem. No problem. I'll try to manage because सब कुछ तो नहीं होता, but कुछ जितना होगा I'll do that.
बिल्कुल sir. Sir, as law of nature says,
Could you
every action
give me
has
the
a
opportunity to
reaction.
ask question?
So if every innovation, every scientific innovation has the same. So that you have well explained. Now I will request Dr. Sapre, who is the chairperson for final comments.
certificate
I request to
वाह
mute
जी वाह।
the microphone. There is some disturbance. Thanks a lot, Bartwal sir. And now I hand over the platform to Sapre sir.
Thank you so much. Thank you so much.
Ji sir. Sir, please unmute yourself.
Okay.
I have unmuted myself. Okay. Am I audible? Can you hear me?
Yes, sir.
Wow. I would say wow. What a session. What an explanation Dr. Bartwal has given. Really a great session for even novices and for those who are already working in the field of nanotechnology. So, like, he has shown everything. He has started from the very basics to the application. So rather, he has given a full circle spectrum information about nanoparticles, starting from innovation of to utility, synthesis, properties, then applications of nanoparticles, how nanoparticles change their color with size, what is the change in the physical and chemical properties with respect to the change in the size of nanoparticles, the various methods of synthesizing these nanoparticles. Really, it was really pleasure hearing you. That it was kind of, I would say, people say that it was gold. I would say it was a